And pulled back up. All right, lesson number 6, App School 5. All right, so let's think for a minute about where we've been and why we're going to talk about what we're going to cover today. We covered at the beginning what an Urbit agent is, or what an app is on Urbit, and what that means and the kinds of things you can do with it in a straightforward way on the system. And once you know that an app is a door, and you're always we're putting the state into the sample of the door and using that to pull things up and access them. In a sense, that's the secret, but it's kind of like draw 2 circles and then draw the rest of the owl. Those are the parts that we kind of been trying to fill in over the past few weeks. And so last week we talked a lot about the front end, which gives you a certain exposure to the kinds of travails you run into when you're developing and you actually want a user interface tied to what you're doing. Today we're going to talk about threads. Threads are probably slightly misnamed. We can think of Urbit code as sort of running in one of 4 different modes. So at the deepest level, you have the runtime, right? Like there is actually a virtual machine that's interpreting everything that's going on, and it does some tasks that aren't really specified by Nock, by what your Urbit Arvo system is doing, but that are necessary for everything to run, right? Like Urbit doesn't care, what language your runtime is written in. It doesn't care the way that it starts. It doesn't care the way that it handles HTTP requests at the level of hardware, for instance. So this is your Nock interpreter. This is your event log. This is your input-output drivers. These are the jets that you've probably heard discussed at some point. All that sits in the runtime. And then above that layer, you have the kernel. So this is Arvo and the vanes. And so this is what we talked about in the second lesson. This is sort of saying, if Urbit is a system, an operating system, what does it provide as available to you? Outside of that, if we're thinking of this as an onion going outwards, the layer outside of that is user space, and in particular agents. This is Gall. These are things with permanent state, which is what we've been talking about, what we've been operating on in essentially everything that we've done in App School. So today we're going to talk about user space threads. The difference in a user space thread is that these are essentially single-use computations, kind of like a generator, but they're able to do more sophisticated things than generators. So this is basically a disposable or a transient operation. And like a generator, it will have access to certain pieces of information, maybe from the bool or the system state, perhaps other things that are provided. But unlike a generator, it can restore the information back to an agent that calls it. So we are going to treat these as disposable computations that we can set up and run on demand, but we don't have to do all the overhead of building an agent whenever we want to do it. Thread is kind of a, if you're familiar with parallel programming and Unix programming and what threads means in that context, arguably thread is not the best name for this anymore. It's kind of drifted from what the original vision was in that regard. I would almost call it more like an IMP or a system dispatch. It's a way of just sequestering a particular computation, saying go complete this for me, and then when it's done, return the value back to me. So it is like a generator in that sense. Now, if we go to, let's go to Urbit. Let's get a FakeSod started up. That running, and let me that back up as well. All right. So yeah, so runtime, Arvo plus vains, user space, gall, and user space, spider or con. All right, that's what we have here. You've run these before, most likely. So some of you will have had to debug a ship, and they'll say, "Well, go run, azimuth load, and tell me what like this is a thread that's used to synchronize your ship's knowledge of the state of azimuth with the knowledge that is on Ethereum, for instance." So this is used in debugging. So anything that begins with a HEP in Dojo is a thread from the FAS/TED directory. The reason we use these things like azimuth load is we do need a moderately complex operation, possibly one that has a lot of input and output, or either at the user or the network level, very commonly at the network level. Sometimes this uses what's called the I/O monad. Those of you who have had some computer science may recognize the word monad. For our purposes, this basically means that it's a wrapped bundle of calculations that are an attempt to make a more straightforward interface for a developer to use, that we can chain these things together. The weakness of a thread, and in some case the reason it exists, is that it's impermanent. As I said, it's not it's transient, but it's also used for processes that are liable to fail unexpectedly. If I'm trying to access something from an API, I don't know if that website's up. I don't know if my request is well-formed or ill-formed. I don't know if there's network latency and traffic issues that might be interfering with what's going on. And so our model for threads with respect to agents, we use them at the command line, but the model we're going to use with respect to agents is that basically you can spin them up and treat them like a call to a different agent, in that when you start them, you'll subscribe to the result. And then when they complete, they will return the result to you as a gift. And you'll be able to operate on it that way. And just get it back in your on agent arm or on Arvo arm and handle that. All right, so anything with a thread, there's a time agent, for instance, that I can give it a time like 5 seconds. So if I run as time and I give it a time, then it'll run, and when it's done, it will return to me the value of that time. So in this case, it ran for 5 seconds, and then this part after the double dots is at the sub-millisecond level of frequency there. HEP code. What happened there? So if you run less code, it gives me lidlet, tabweb, pillx, ridrup. So this is the standard code for any Zod. You'll notice what actually happened from the output here is that it did this weird print, and it kind of turned sideways, like every character was on a different line. Something's funny about the way that the pretty printer handles the return from threads. And so if you get a tape return from a thread, it prints every character on a different line. I don't know exactly why that is, but there's a code thread that does basically the same thing as less code, but you might use it in a context where it's not convenient to use a generator. How do you use a generator from an agent? We don't have a good design pattern for doing this. Dojo's well equipped for this. What can you see? Can you see my VS Code screen where I've been typing here? My terminal's at the bottom of that. Yeah, Daniel, you may need to mess with the zoom settings to get that to show if you zoomed in previously from other discussion, or scroll to the bottom. It's another one of these weird aspect ratio things because I'm trying to fit everything on my screen. Someday maybe I'll go back to to monitoring it, and then it won't be as big of a deal. But for now, I live in landscape instead of portrait world, unfortunately. All right. All right, so let's take a look at threads. All right, so if you go into, this is echo from last time. We don't need to see that. We just need to go into Zod, into the base desk. There's a TED directory. All right, if you open TED, you'll see there's a lot of threads that are down in here. There's the code thread. There's time. Let's open up time and just see what's going on with time.hoon. So this is fazted faztime.hoon. And it's the one that I ran a moment ago where I gave it a time and I let it run. And if you try and type something while that's going on, it generates this error message that it's hanging the Dojo. So Dojo is blocking in that if you start a thread, as long as that thread is evaluating, Dojo will not take subsequent input. Fortunately, with an agent, that's not the behavior you're going to get, but with Dojo, that's what you'll see. And so it tells you that the solution is to press backspace to abort the thread. All right, here's a thread. Now, what you'll probably notice looking at this is that this is kind of a bunch of dense code. There's a lot going on here. For better and for worse, there's currently a lot of boilerplate required in threads. I'm in favor of simplifying these and trying to move some of this material out so that it gets automatically handled the way that a generator can just be a gate and you don't have to worry about a lot of other things with it. But for now, basically everything above line 8, line 7, and up is boilerplate, and you're going to repeat it or something almost identical to it in every thread that you ever write. So what we're doing, we're importing spider structures that we will make reference to, like strand on line 3. And what Sir Spider, I guess I can annotate this over here, Sir Spider. What Sir Spider does is it defines a strand and a thread and some other things, but basically it defines a thread, which is the return type out of 4, as a gate that should accept a vase and return the form of a strand that produces a vase. That's kind of a complicated way of saying it, but basically it's doing type checking on the line 4. Thread Spider is doing type checking on line 5, and this is line 7 here, where it's making sure that the information that goes in and the information that comes out are the right shape. Because this is Hoon, this is a little bit more complicated than it would be in a language like C, where you explicitly specify your return type in a function declaration. Like I say, this is boilerplate in that, once you don't really need to think about a form, you just need to make sure that you return something that's wrapped in the right way when you bring it out on the other side. There's a Strand.io library. This has a lot of convenience functions in it for operating on things like scries and network calls and unpacking JSON returns and these sorts of operations and working with these. Now, your main input here is a vase. What is a vase? Right? You probably briefly saw this at a couple points before. Maybe we've talked about it in here. This is the problem with teaching several classes as I start to cross wires. I know I've talked about this recently, but I'm not sure if it's with you. So what is a vase? Do you remember running into these, like the type sphere, for instance?
Type and value.
Yep. So it's a pair of type and value, type and data, like however we get it. So we give it, here's a hexadecimal 0. It keeps both part of that information for me. And it's interesting because the value is actually just stored as the raw value, like the raw atom in this case. And all the ARA, the type information, is pushed over to the left-hand side. Now, it turns out that for a few reasons, we use VACEs all the time in Urbit. It's a way of transmitting information about the type of a value and the structure of a value separately. You can break those apart from each other. So you have the data as a structure, and then the associated type, and you can handle these separately and then put them back together when you need to take them apart, whatever. A thread receives its information, its argument in this case, like in line 5, as a VACE, as a pair of type and data. And one of the reasons for that is that it helps us to actually unpack the information later on and still know that we're getting things in the right type when we pull this out on the other side. So if we create a VACE by using ZapGar, we unpack a VACE by using ZapGal. And so we end up, if we're demonstrating this, we end up using kind of funny little statements like this. I can specify SIGZOD like that. This ends up round tripping what's going on. ZapGar, PAT-P, ZapGal, SIGZOD. It's a round trip of the value, but what we've done is we unpacked it into type and value, and then we reapplied it into our expected type, which was PAT-P. If the expected type of our argument is a pair of null and a PAT-DR, then what is Dojo doing? So if I run FAS_time without a value here, it crashes on line 8. And so it actually crashes at this quantity here, because if I don't provide any input, any argument here, then the value that's handed off to this by Dojo is a unit, and the unit's empty, and so there's no way to unpack the value in the unit. And so this is what ultimately we are doing here, is we are reapplying the value PAT-DR to the VACE to make this work. Now, let me see what a PAT-UD of SIG S5 is. Okay, that's actually a fairly large value, because if you play around with time, then you'll find that Urbit is capable of representing extremely small values in time. So what I could do is I could run time and give it this value. Okay, so it actually fails because it's coming in as a PAT-UD instead of a PAT-DR, and it breaks at that point. So I actually have to get the type right going in to specify this. Yep. So then that converted back to the 5 seconds, and we get our value back out there. So that's what's going on with this. We're unpacking it here. TISLUS. You have likely been accustomed to statements like line 6, TISFAS, to define a value where we give it a name, a face, and then a value. TISLUS is similar, except that it lets you sort of just implicitly wrap the values in. It just lets you pack them directly into your current subject. This is interesting because, for one reason, I can add the value 1 to my subject, and I can refer to the current head of my subject, which is the value 1. There's no face on it. There's no name attached to that value. I can only refer to it by position, which is it's currently at the head of my subject. So TISLUS is not as commonly used in Urbit now, but you do still run into applications. For instance, when you want to unpack things, or when you have multiple names you want to apply to values in a tuple, for instance, where you may still use TISLUS, where that may still be the more convenient thing to do. All right, these next 3 are kind of where the the magic happens, in a sense, right? Like this is where something different happens from what normally goes on in Hoon. Normally, typically in Hoon, you calculate a value, and the moment that that value is done, it hands back to you and the expression continues. So even if you're writing a complicated expression in Hoon, you have a sense of, well, this may take a long time to calculate. But you don't really sort of have an active sense of where in this calculation might my active part of my process be at any given time. Well, to do something like measure time, we actually need to do that. And so we are going to use a pair of things, which is a new rune called mikgal, and the bind method from Vase, which is a piece of the strand that the Vase gives you. These are always used together. So you're always going to see mikgal and bind in the same statement. It's another one of these boilerplates that's really common. And what mikgal is doing is it lets us build a pipeline of dependent clauses. So first off, if you look at mikgal, how many children does mikgal have? How many sub-expressions does mikgal anticipate?
3.
Everyone's going with 3. But what's always missing in, 4, right? Because you're always missing the next line, right? The continuation of the expression in Hoon. So our definition here is going to be, mikgal is a way of saying, ignore these first 2 for a minute, because these are just a way of capturing the expression. There's one expression that is it's kind of it's an independent clause. It's an independent expression. And then whatever follows it, in this case, the rest of the program, is a dependent expression. It depends on the value that the first expression is giving you and that this first expression complete. So get time has to go look up the time in the system. It's getting now, essentially. All right, so it's going and it's looking it up in Arvo or whatever it needs to do. We can go look at Strand.io, get time in a minute. But this is what it's doing, is it's going and it's looking in Strand.io and it's saying, get me my current time. When that value comes back, however long it takes, it is bound to the name now1, to the face. And then, and only then, does the dependent clause continue. Now, it turns out in this case that the next statement is also a mikgal, so it has an independent clause, which is to wait for some amount of time. And we'll be curious to see how this functions. And in this case, whether or not this returns anything, we are not binding it to a face. So maybe it returns something, maybe it doesn't return something. We don't care. We're throwing it away, whatever it is. And then we're repeating our first call with an independent clause, with an independent clause and a name, a face to bind to the result of that, and then a dependent clause. The dependent clause, now, this is kind of a complicated piece, so let's start from the inside out. So first off, sub now2, now1 is saying, what is my ladder time minus my starting time? In essence, what is the duration that I actually ran for? Which is guaranteed to be at least 5 seconds, at least my time, but probably will be slightly more because the rest of this calculation does take a little bit of time. Then I'm casting it to a patdr, and I'm invasing it because this is what Pure expects. And then Pure is returning for me a value. This means that I produced a strand, this result type that's coming back out. That does nothing except return a value. There's no input or output. There's nothing sent forwards or backwards. It is just a value of this vase, right? So Pure expects to return you a vase. All right, and then Dojo is going to unpack that on the other end and give it back to you. It's just a number here. So that's how we count time in Hoon. If I put, longer times, shorter times, whatever, this is all just sitting on top of how long this takes because of whatever sleep strand IO is doing. So let's jump over to sleep strand IO. Let's look at, we'll just do the strand IO library, and then we'll come back and start composing some simple threads and see how those behave. So now we'll go to lib strand IO. And there's a lot of things in it. You'll notice like there's a get time. Well, how does get time work? Well, it actually wants the bowl from the input thread. So it looks like a thread automatically gets the bowl. And so it's just looking at that up, and then it's returning it as a strand shaped, or as a form shaped item inside of strand. Whatever, we actually don't care, right? We just know that this is the sort of thing that you need with McGal. If we're getting hour, which is our ship identity, if we're getting entropy, whatever, they all have the same shape. There's a done head tag that's returned with the actual value. Then there's a lot of handlers for various things, various different kinds of gifts that you can get back from Arvo, return values and so forth. All right, here's sleep. All right, so sleep is also a McGal, and it's running get time, and then it's running wait to add now to whatever the duration is. So it adds the current time to the duration and runs wait. So let's see what wait does. Take wake until. When you start working deeper and deeper in the Urbit stack, you can end up following these chains to figure out exactly what's going on. There's definitely nothing wrong with writing these down or drawing these out to figure out what's going on. Now that we've gotten to the bottom here, what looks like the bottom looks like we take a thread, and then we are actually waiting until Bane. We're going to send a value to Bane, which is waiting for a wake value. And when we get that back, if it's a done, if there's no error in it, then we return a done at the point when there's no error in whatever's returned from Bane. Now, the advantage of strand IO is that you can write a statement like this and sort of not think about what's going on under the hood, as opposed to, clicked in the wrong spot. As opposed to springing something like this on you, where it's just like, oh, you send a message to Bane, send a card to Bane, and you subscribe through the result, and conceptually you understand what's going on. You've done this in the previous homework as you've worked through this. But in practice, you look at this code, there's a lot going on here. And so getting used to the kinds of affordances that strand IO offers you are, I think, pretty important here. So you can just write, sleep strand IO, and it takes care of that value for you. All right, let's look at a simple agent. All right, so this one, let me go ahead and save it as Ted simple.hoon. Let me add a line at the beginning here. What's that? As simple.hoon. All right. And I'll paste this in the chat for you. All right, so import our boilerplate, Tizcom, expose everything in strand spider, but name it strand, rename it strand when we refer to it. It's going to return a thread spider. We receive an argvase, right? All this is the same. This is your boilerplate, these first 8 lines here. What it's going to return is pure M of a vase. In this case, the vase is the argument. So this should just return the argument. This should just echo essentially whatever we say to it. So bar commit base, I should see, looks like I modified time at some point in simple, but if I run simple and I give it no input, then fine, nothing happens. There's nothing to say there. If I give it a string hello Mars, then it returns to me a unit of sig and hello Mars. And, you know, otherwise there's not a lot to do with it. This is the trivial thread. This is the simplest possible thread. This is like our original alpha when we started looking at Dojo. Any non-trivial thread is going to use mcgal and bind. So we've run into those. Putting bind another way, if we go back and look at bind here, the argument of bind is, if I'm going to explain this in kind of a more Hoonish way, or I guess Knockish way, there's a bind. It takes two gates as input, as arguments, and sample. So it calls the first function, the first gate. And if it succeeds, if it doesn't get back an error of some kind or a crash, then it calls the second with the results of the first as its sample. So that's attaching the face to that result, and then now it's in the sample, and I have access to that quantity and any of the subsequent values there. That's how to think about what bind is doing for you here. So if we wanted to retrieve a value from a public API, let me save a copy of simple here. So we're gonna write this one together. So this will be pokédex.home. So we're going to write one that is going to retrieve a value. If you've ever seen pokeapi.co, pokeapi.co. This is a website that exposes information about all the Pokemon that ever were in JSON format. But it's really nice as a demonstration, because we can just hit the API and pull information, and sort of, you know, it's sufficiently differentiated that we can get this JSON back and then actually decide what to do with it. So everything up above this point, this is my standard boilerplate. I can copy paste this, and besides maybe adding libraries or whatever, I can copy paste this in anything I make from now on. Now, I have to think about, if I'm going to use that zapgal on my argument as an input, what is my argument likely to be? It's probably going to be some kind of text, right? Like, so the way I might want to use this, let's say there's a usage clause here, is I would want to say something like Pokédex Pikachu, and then it returns to me, you know, here's the whole stats, whatever the JSON of this actually returns to me, which we'll see in a moment what that looks like. And then it would just return to me back this value. So this is the way that I'd like to use it. So I'd like to use it with a pat t. So if I give it a not or a term instead of a chord, it should just work. But I can't give it a tape. If I give it a tape, that's not a pat t, and it'll break what's going on here. All right. So my call is actually going to be pretty straightforward. The call is actually just going to look like this: fetch JSON strand.io of some URL. Like that knows how to go out, request information over the wire, get the information back, and unpack it as a JSON type. It does all of that for me conveniently. I just know that I'm going to get a Hoon JSON back. It doesn't do the reparsing. We talked about the reparsing a couple weeks ago, but it does give me these values back. So for convenience, what I'm going to do to build my URLs, I'm going to have a base URL, and I'll give it the actual API, which will look like this. Let me put a slash at the end just to save some trouble there. I'll give you a copy of this in the chat in a moment too. And so then my URL should be welding the base URL to a tape of my argument. I may want to make the modification that I'm lowercasing, which is CAS, the value. So this is going to convert my argument from a chord to a tape, and then CUS uppercases. So CAS is the opposite of that, lowercase is it. So lowercase it and then weld it together. So if I type capital P Pikachu, all caps Pikachu, that all goes to lowercase Pikachu, which is what the API expects. Then I'm going to mcgal. I'm not going to worry about my return type yet, but I do know there's a bind M. And I do know that there is a fetch JSON strand IO, and I know there's going to be a pure M that's going to return some sort of vase. Now I know what I'm getting back is a JSON because it's coming back from fetch JSON, and that's what fetch JSON gives to me. So I'll just call this info. Info sys JSON, and I'll just return info. And if I've done this correctly, so I should be able to say Pokédex. I don't actually know Pokemon other than like the common ones, but we'll let that run for us. Okay, so it runs. Then you see that it's marking for us that it's doing HTTP transactions in the background. It's probably already retrieved everything, and it's actually probably spinning on. This is going to be a lot of information because every Pokemon game that's ever existed has information, right? Like has some of this content in it. So I probably could have picked some less popular Pokemon whose name I don't know and got a much smaller result. So it'll spit out the whole JSON here in a moment. But it looks like it's not crashing, which is great. So there's that value there. Yeah. So it'll return a raw JSON from fetch JSON. If we wanted to use it, we'd have to feed it into a reparser. But like what this has made easy by writing this thread is that all of the complexity of the network input-output request is reduced to what this thread is doing, which is basically line 14. And then if we want to use this inside of an agent, we're going to be able to reduce this to a single line in the calling agent and then a handler when we get the value back. So we'll take a look at that in a minute. What would it look like to do this? And your homework's actually going to be implementing a simple agent to track these requests, not just sit on them. Yeah, I think this is the pretty printer that's running quite large there. JSON parse error. It's possible that they've done something in their API that changes the result of that. I had this working earlier today with a different Pokemon. Let's see if I can get it to. I don't know, what's like a really unpopular Pokemon that's only in like one game? Someone help me out here. Diglett, okay. JSON parse error, why are you failing on this? All right, fantastic. We are going to do some sleuthing to see if we can figure out what's going on. There's an occasional bug that you get in parsing when you have uppercase values in quantities. So let's jump over to here /Diglett. So this is like what the raw, did they change the, they've like moved some, maybe they upgraded their API to v3. I had this working earlier today and it was like behaving properly. Yeah, HTTPS, pokeapi.co, Faz API, Faz v2, Faz Pokemon, Faz. Let's try Ditto. Oh, well, okay. Two T's at the end. Okay, okay, there we go. So now we are actually getting that back. All right, so if I run it again, let's see if I get a value back. Besides a JSON parse error. Right, I don't have any error handling in this. So it looks like, yeah, this could actually be a pretty big, complicated file, depending on what's in it. Or it could just be Urbit being slow. But yeah, so anyway, so it's the thread should give you this information. Why was it failing on Pikachu though? That doesn't make sense to me. Oh no, it's succeeding now. I wonder if it just ran into something too big. So the other thing that can happen with these, that's normally in the reparsing though. So if your JSON names are invalid terms, your reparser can have trouble with them in certain cases because you can't represent it as a pat TAS. But not clear to me that would be the case here. This looks like valid JSON to me, everything that I'm seeing. Okay, so it is working in some sense, but it's failing to parse on at least some of them for some reason. I guess a zap call might give us a better output of that. The other thing we could do that would be helpful, in general, I think Urbit's debugging tools are a little too simple because we don't have breakpoints. It'd be nice to be able to set a breakpoint and run line by line and see where this is actually running into trouble, like step into fetch JSON and watch that play out. Yeah, because it's still just grinding on, can it process Diglett, which didn't seem like it was that large. Oh, there we go. Yeah, okay, never mind. Turns out Diglett is huge. So I guess Pikachu would have even more of that problem. Yeah. So, okay, there you go. So we can actually retrieve this information and do something with it. That's probably another big one. Anyway, I'll abort and not worry about running those. In principle, right? Like you get the idea. What's actually slowing it down then is the fact that we're dumping the output straight to the screen, it's not the parsing and it's not the retrieval, the network retrieval is taking forever. It's the fact that printing long output is just really slow in Urbit for reasons. Okay. Is yours not being slow? Okay, fantastic. I have had people comment that my Urbit is slower than they expect in some regards. So I don't know. I don't know what I've done. Okay. Calling a thread. You've seen how to call a thread from Dojo, just with the HEP, and it works for the base desk. If you have something on a different desk, like if we have like a sandbox desk, then you would prefix the desk name with a zap at the beginning. Yeah, maybe. And so you can call on desks besides base by specifying your thread path this way. This works for generators too, by the way, where you can call them at a different location. Within an agent, what you're going to see is code that looks like this. Let me actually switch this tone and make this a little bit smaller so I can fit it all on the screen. Let me turn off word wrap. That'll help. Okay. All right. So great. What I'm going to do, so this is like in an on poke arm or something. What I would do is I would generate a random thread ID. This is going to be your identifier. And in this case, I'm also generating a random label for it, so I can do it with a label. And I'm generating starting arguments for it. You'll notice that this is a unit, just by the conventions of what's expected here. I've pulled in information from my vase, whatever I've received at this point. I'm handing it information. This is an actual call that's in an agent. So this is sort of setting up labels and names for things. And then I have been favoring this syntax in App School, but it's the same as the other. Nothing strange there. So you're going to pass a pair of cards to an agent on your own chip called Spider. You're going to pass it with a unique label for the thread that you're running. And you're going to send it a watch card. So you're going to subscribe to the result at fastthreadresult / whatever your thread ID is. So you're going to subscribe to that result. And then you're going to poke Spider to start the thread with the arguments that you want to go into the thread. It's a two-step process. It will complain if your thread ID is not unique, the same way that you get error warnings about like not having unique wires, not having unique identifiers for subscriptions. It's going to complain about having unique thread ID. So you're going to need a unique thread ID and you're going to need a unique wire generated in whatever way. So in this one generates it from the current timestamp, identifies it that way, and then it names it with thread cab entropy. If I run Scott senuv on a hash of my entropy at any given time, great. I have a unique value that is different from any other value that anyone will ever generate in Urbit. So that's a thing that makes that unique and always identifiable and not really subject to collisions on any statistical level. When this returns, it's going to come in back via the on agent arm as a fact. So you receive things back, if we go back to Delta or whatever, you receive things in an on agent arm, which we haven't really been doing a lot of. Let's take a look at Delta. Yeah, let's look at Delta app. There's Delta. Actually, let's look at Delta follower, because Delta follower did get things in its on agent arm. So say you're on agent arm, you're going to receive things back. And one of the things that you switch on is the kind of thing, the head of the kind of thing that you switched on. It's called a sign. It's basically what did you get? What did you actually get back? Is it a watch acknowledgement? Is it a kick? Is it a fact? What is it? All right. So if it's a fact, then it's some value that was handed back to me, give fact, and I've received this value and I need to do something with it. When you're coming back from a thread, it's actually going to be labeled not fact, it's going to be labeled thread done. And then you're going to get the same information, and have to decide how to process it as thread done. There's a thread guide that walks you through all of this in detail, piece by piece. It also includes like how can a thread spawn another thread, and you can do parent and child threads and all sorts of fancy things. At the app school level, we don't really need to get that deep into it. We just need to know how do we dispatch something and bring that value back to us? Okay, so spider is essentially the way you do it. Now, there was also a vein that I mentioned that would work with everything. Con is newer than spider. Spider is actually a Gall agent, and in some ways, Con has a slightly easier interface to work with. It only requires one line because it automatically subscribes you, so you don't have to send a watch and a poke card together. You can just send a poke to Con, and it'll handle everything for you. So the two equivalent lines between those would be something like this. So for Gall spider, if I were passing something to azimuth load, I would pass it the watch at the thread ID, and I'd pass it a poke of a spider start to start it to spider. If I were doing this to Con, I would pass it a thread name, a desk, and a thread name, and then the return type as a mark, which is typically noun, and then some value. In this case, like there are no arguments to azimuth load. So if I wanted to trigger azimuth load, this is all I would need to do to trigger azimuth load. If I needed to do the same thing from Gall, it would happen this way. The one difference is that this is a vein, so it returns its on thread, or its thread done through on Arvo. And this is an agent, so this is going to return thread done through on agent. So there's some little subtleties. Con is newer, and in the medium run should probably take over everything. Take over all of these. There's this task type here that you'll run into. It can be one of three things. It can be a fard, a fired, or a lard. All of them lovely names. This is a regular in Arvo thread. This is, something in TED is what that means. A fired is initiated from the outside. So this is if you're invoking the thread using something that's talking to Urbit. So you can actually start a thread from outside of Urbit. You could write a front end that would talk to the Urbit runtime and maybe trigger something and get its value back, and that would be a fired thread. And then a lard is an inline thread definition. And the way that would work is I can actually define a thread as a value, like Tizfaz shed is a thread here. And in this case, it's a little bit simpler. It is a strand base, it's a pure M. And it does have two calls, one to Helm high, or one is a Helm high, and this is basically just hello world code in both these cases to output these things. So it's poking us with the text high there. And then it'll pass this to Con as an inline thread defined right there. The nice thing about this is this does handle the boilerplate a little bit more simply, and we can see what we're calling right there. Sometimes this is more convenient, sometimes this is not, but that's a judgment that you can make with respect to that. Con, as I said before, is newer, and so we have probably not seen the final form of what threads will look like. However, if you are accessing data over a network or with I/O, and things are likely to fail, a thread is your best approach to doing it to keep your agent simple. So it lets you take a lot of kinds of things that you might do in an agent and push them off into a thread and simplify your agent code because you've sequestered that code somewhere else. One more of these I wanted to look at, which was code.hoon. So we saw the way code.hoon worked earlier. You know, like lus code, I can do hep code and it'll give me back whatever my code is there. What actually happens here, boilerplate above line 7. Then I'm going to mcgal, I'm going to get bool. So I'm going to get my bool. Like what is my bool, right? It's my identity, it's my timestamp, it's my entropy, maybe a couple of other bits and pieces of information that it's that standard information that a thread can see. And then I'm going to scry into jail with the name of my current ship. You'll notice that I'm not doing this with a .ket. I'm doing it with the scry operation here. I could probably do this with a .ket. I don't think there's an obvious reason why that would not work for me. So most likely that's ultimately what this is wrapping is something that is a .ket or looks a lot like a .ket. But that scry needs to resolve, and then everything else down here is let me strip off I'm going to turn it into something that looks like a patp, but a patp starts with a sig, so I'm going to strip off the sig. I'm going to take the tail of everything after index 1 to the end. So I'm throwing away that information. I'm throwing away the sig that's at index 0 in that tape. And then I'm returning a vase of a tape, and everything just gets passed all the way out, coming out of here. So that's what this looks like with a scry operation here. Let's actually look at that scry really quick just to see what. I suspect nothing fancy is going on with it. You will notice that we're not actually giving it with a scry. Normally we give it the ship and the timestamp, and it looks like we're not explicitly supplying that at the head of the scry. So let's see. I want strand IO. Okay, so it is doing a .ket, but it is supplying the identity and the timestamp first. So it's taking the char, I guess it's the pair of the char, the vane and the vein, or the vane and the char, depending on which vane it is. Then it's taking the head of the path. Then it's taking everything else as the tail of the path as those values. So it does kind of a weird unpack, but it is ultimately a .ket that's trying to save you some trouble in doing that. So, you know, strand IO, strand lib, or strand lib. Maybe it's strand is the one strand's the one I'm thinking of. It will save you trouble if you sort of treat this as a standard library and learn what these quantities are and learn how to pull them in and approach them. So let's see, what questions do you have coming out about threads? Your homework is going to be writing a Gall agent that takes the Pokédex thread, which we just wrote, and uses the agent to call. So you can poke the agent with the name of a Pokemon. And if you do not have a local copy of it, then use the thread to retrieve the information. And if you do have a local copy of it in a map, then produce that value. That's the basic idea of what you're trying to handle there. So I hope you can kind of see, even if you can't see the particulars of it, you can see the shape of how you would do that using threads. The next two lessons, which I may very well collapse into one lesson, I've been debating back and forth on whether or not to just try and roll all of the 8th lesson into the 7th lesson. They're going to have to do with, like, okay, you've built an app. Now what? Like, how do you distribute it? How do you publish it? How do you test it? How do you what are libraries you should be aware of? What are some of the design patterns that you should be using and things? So we may look at some code and some agents that are published, and and give you a feel for that. But, by the time you're done with that, you should be able to write some agents with simple front ends and, take a look at things like Ahoy by Midden Fabler. Is a good example of an agent that's about the size of agent that you could produce at this point in App School, and definitely by the end of App School. That's a ship monitoring. So what it does is at the time interval you specify, it pings a ship to say, is this ship still running? So it's just a way of tracking, is an Urbit ship running? Every hour I want to see if my star is running. If my star is not running, then send me a DM and let me know that something's gone wrong, or send me a notification. So, these are, now that you know how threads work, how front end works, how agents work, it's a matter of putting these pieces together in various ways. So that's where we're going to go after today, as sort of how do we publish, and then what do more mature agent models start to look like. Who will debug Pokédex.hoon, us or you, so it actually works? Well, mine actually worked. Did you copy paste, or did you type it from what I was typing here? Okay, I'm wondering if you didn't do the cuss to lowercase the input. So I had a line where I cussed the trip of the arg, or sorry, CAS. Yeah, it's going to be something really similar to that probably. So the version that I have here and the version that I have in the notes works. So compare to that, or just copy what we have from that, and you should have a case that does work correctly. It would be interesting to know what's going wrong in the one that's failing to parse the JSON that you're running into. It also could be something like, if there is some network latency or it's crashing, then this may still show up as a JSON parse error when that value comes back. Where errors actually resolved can be kind of funny sometimes, but we'll get that figured out. So, all right, cool. In that case, see you all next week.